In this video, I'm going to introduce you to node voltage analysis. The objective in node voltage analysis is to solve for all nodal voltages in a circuit. The reason we would want to do this is once we have all the nodal voltages in a circuit, we can calculate any voltage, current, or power in the circuit, so we can know everything that's going on in the circuit. So, for example, if we have a resistor connected between nodes X and Y, we can easily get the voltage drop if we know both nodal voltages Vx and Vy. So Vxy, for example, is oriented with the plus side here on the left and the minus on the right side. Vyx is oriented in the other direction. These are the equations for Vxy and Vyx. You can also get the currents Ixy that flows from node X to Y by using Vxy divided by R, Ohm's law, or you can use Ohm's law to get Iyx using Vyx and R. And you can get the power delivered to that resistor also using P equals Vi, but you have to follow the passive reference convention, as always when you're doing Ohm's law or power calculations. So briefly, let's go over the steps and then we'll apply it to an example. Here are the steps. First, we identify all the nodes. When we do this, we get to pick a ground. You get to choose your ground. Pick a ground, any ground. The best choice is to pick the ground that is connected to the most independent voltage sources. Then, once you do that, you have to figure out which nodal voltages are known and which ones are unknown. I list here extraordinary nodes, right? An extraordinary node is one that's connected to 3 or more elements. Normal nodes, ordinary nodes, you can just you don't have to worry about them so much. But they can be helpful, especially if they're connected between ground and a voltage source. For each unknown extraordinary node, we're going to write a Kcl equation. We're going to express that Kcl equation in terms of nodal voltages and resistances and any known currents in the next part of that step. And then we will use algebraic techniques to solve for each nodal voltage. And once we know the nodal voltages, we can solve for any particular current, voltage, or power that we want or need. So let's illustrate this with an example. Here's a circuit. 2 voltage sources, 1 current source. It may look intimidating. We will first identify the nodes. I am going to call this extraordinary node A. I'm going to call this one B, but I'm also going to identify B as ground, V equals 0. And then we have 2 non-extraordinary nodes, ordinary nodes, and that's fine. Let's look back at the procedure. We have done step 1. We've picked our ground. Now we're looking for known and unknown extraordinary nodes. Well, because B is known, its voltage is 0. We defined it to be ground, so that makes it known. A is unknown. We do point out the fact that we know this is, let's call it C, I suppose, VC, 6 volts. We call this one D, then we have VD, 12 volts. So we just have one unknown node, one unknown extraordinary node. So that's the one variable that we want. So we have one variable, we need one equation to solve it. So how do we get that one equation? Well, we use step 2, or 3, I should say. We're going to write a Kcl equation for that unknown nodal voltage. So let's assign some currents. I'm going to assign a current going this way and a current going that way. So this will be IAC because it's flowing from A to C. This is IAD because it's flowing from A to D. I'm also going to assign IAB because it's flowing from A to B. Now, from Kirchhoff's current law, those currents must sum to 0. One thing I'll point out here is that I have complete control over the currents that I choose. They're an arbitrary choice. However, I need to be consistent about how I treat them. So when doing Kirchhoff's current law, I need to pick a formulation like all currents leaving algebraically sum to 0. So I chose all currents leaving the node A, right? So let's just write out an equation. those have to be equal to 0. The next step, as we look at step 3, is to turn this into an expression in terms of nodal voltages and resistances and known currents. So, for example, we know that IAB is -2 because 2 amps flows up, but IAB is flowing down, so it's -2. We can see that IAD is going to be VAD over the 3 ohm resistance in between. That's Ohm's law. And then IAC is VAC over 6 ohms. Now, recognizing that VAD is VA minus VD, and VD is 12, and also recognizing that VAC is VA minus VC, which is VA minus 6 volts, since we know that VC is 6. Okay, so we can manipulate this a little bit more. And it's clear from this manipulation that we have one equation, one unknown, so that's enough to solve the problem. So I'm going to manually solve this now. I'll multiply everything by 6. That gets us 3VA equals 42, and that gets us VA equals 14 volts. So we'll just annotate that. Now that we know all the voltages at each node, it would be easy to tell me, for example, what VAD is. And it would be easy to tell me what IAC is. So let's just show that. Well, VAD is 2 volts. And IAC, well, that is VA minus 6 over 6, 8/3 amps. Now, we might want to just verify, does this answer make sense? And we know that 2 amps goes up here. We now say that 8/3 amps goes this way. So we should expect whatever goes from A to D should be the remainder of 2 amps. So let's just see what happens here. Right, and so the claim here is that IAD and IAC, they need to sum up to 2 amps, right? Because 2 amps flows into A, and then these other currents, IAD and IAC, leave, so they have to sum up to 2. And IAD is 2/3, and IAC, I've made an error, that should be 8/6 of an amp. This is 4/6. So when you add 4/6 and 8/6, you get 12/6, which is 2 amps. So we now have a pretty good sense that we got this problem right. We did a dummy check, and it passed. Okay, so that was a simple example of how we identify the nodes, pick a ground, identify the known nodes, write a Kcl equation for unknown nodes, use Ohm's law to write the Kcl equations in terms of node voltages, and then we have a system of equations that we can solve, one equation for each unknown nodal voltage, because there's one Kcl equation for each unknown node, and then we can solve for any desired quantity in the circuit. I hope you found that useful. If you did, please like the video, subscribe to the channel, and have a great day.